Today we're going to talk about heaps. A heap is a binary tree. It's always a complete tree. It is not a binary search tree because the left child does not have to be less than the parent and the right child greater than the parent. We have two different kinds of heaps. We have a minimum heap and a maximum heap. In a min heap or a minimum heap, the parent is smaller than the children. And I have here this diagram 1, 2, 3. I could just as easily have had 1, 3, 2. Again, the left child does not have to be less than the right child. With a maximum heap, the parent has to be larger than the children. 3, 2, 1 or 3, 1, 2 is equally fine. So to insert into a heap, first we put the node in keeping the correct shape, meaning keeping it a complete tree, and there will only be one place where we can put a node to keep that right shape. And then we reheap it so that the parent nodes are smaller than the children. That's if it is a min heap. If it's a max heap, we reheap it so that the parents are bigger than the children. We'll do an example, and we're going to put these integers here into a min heap. So her first number is 40, and there's only one place that can go, and that is the root. And then we have a 23. There's only one place that can go, and that is the left child. And that maintains the structure of a complete tree. Now we look to see if it's a heap, and it isn't, because the parent is bigger than the child, and we wanted it the other way around, and so we must switch the 23 and the 40 over here to make it now a min heap. I put the 30 in here to show you that the only place it can go is to the right of the 23. That maintains complete tree. But now I have to think about my minimum heap. Is it okay? And the answer is yes, because the parent is less than the children. So that's fine. And now the next thing to go in is the 19, and the only place it can go is the left child of the 40. Again, maintaining this as a complete tree. And now we have a problem because 19's parent is 40 and 40 is bigger than 19. So now I have to move my 40 down and my 19 up. So now my 19 is less than my 40, and that's fine there. But going up again, 23 is bigger than 19, so I have to swap those. So my 23 comes here, and my 19 goes up here. Now I'm back to having a minimum heap. The next thing that goes in is 50, and the 50 is going to go in as the right child of this node, again as the only place it can go, and maintain the complete structure, complete tree. Okay, so there's my 50. And then I have, let's just make sure, yes, everything's okay. And then I have a 14, which is going to go in as the left child of 30. Why here? Because again, it's a complete tree. But now 14's parent is bigger. So I have to swap those. 30 comes down. The 14 goes up. And now 14 is less than 19, so 14 goes up and 19 comes down. And then the next one to go in is the 12. And 12 is going to go here as the right child, again, to maintain this complete tree. So the 12 is going to go in here. But 12 is less than 19, so these are going to be swapped. and then 12 is less than 14, so these are going to be swapped. Oops, that was a 14. 14. And then 45. So the 45 is going to go in as the left child here because that's a complete tree. And since 45 is bigger than 40, I don't have to reheap. So here is my heap. It's looking a little sloppy, but every node, every parent is less than its children. I've written it out more clearly here so you can see the result. You can see clearly it's not a binary search tree, and so it doesn't help us to search. And you might be wondering now why on earth we're using a heap in the first place. Well, let's just do some deletes and then we'll see if we can find a rationale for this. The delete algorithm says delete the information from the roots and then take the information from the last node and put that into the root and then reheap if necessary. So the first thing that will come out is that 12, the 12 out. And then my heap is going to look like this. I deleted the 12. I took the 45 because that was the last one. In fact, the only one that I can remove from this heap and still have a complete tree. So I took the 45 and that now goes into the roots. Now the problem is it's no longer a min heap, so I have to reheap. I need this to be smaller than its children. So what I do is I pick the smallest child and I swap. So 14 and 45. Pick the smallest child, that's the 19, and swap it with the 45. And now I have a min heap again. But I'm deleting. So the next thing that I delete is the roots. So I drew this out again for you. I deleted the root or the information from the root, which is the 14. The 14 goes into the output and it's replaced with 45, which is the information in this node here. That's the only node that I can remove, maintaining the shape as a complete tree. So that 45 went up into the roots. Everything else stays the same. Now I look at it and I say, is this a minimum heap? And the answer is no. So I need to alter some things. I need to swap my 45 and 19. Yes, 19, because 19 is smaller than 23. And then 45 is bigger than 30, so I have to swap the 45 and the 30. And now I have a minimum heap again. And now it's time to delete something, and the thing that I delete is going to be the 19. And the thing it's going to be replaced with is the 45. So here we put the 45 in the root. We took the 19 and we put that into our output. We deleted this node. We put the 45 into the root. And now we look at this and say, is this a minimum tree? And the answer is no. So I need to swap my 45 and my 23. And this 45 is bigger than 40, so I swap the 40 and the 45. And now I have a minimum tree again. And I delete some more, and the next thing that gets deleted is the number 23, and the thing that goes into the root is 50. Again, why 50? To maintain this as a complete tree. So here is our output so far, and this is the result of deleting the 23 and putting this 50 up into the roots. Still a complete tree, but now we have to reheap. And so we look at the 50 and we swap it with its smallest child, which would be the 30. So the 50 goes in here and the 30 goes to the top here. Okay, and now I need to delete, so I'm going to delete the 30 and I'm going to put the 45 in its place. So the 45 is going to go here, no longer here, and I'm going to output 30. So I output my 30 and now I have this tree still complete, and I need it to be minimum heap, so I need to swap that 45 and that 40. So the 45 comes down and the 40 goes up. Delete again, so the thing that gets deleted is the 40 and the thing that goes in its place is the 50. So here is our output. Just outputted the 40, put the 50 in the place 40 used to be, and now we see that it is no longer a minimum heap, so I have to swap this 45 and this 50. And now it's time to delete again, and when I delete this time I'm going to delete the 45 and put the 50 in its place. It's 45 and then 50, and if I look at my output, which I can just bring down here, there we go. If I look at my output, I can see that it is sorted, and in fact this is called heap sort. Not good for searching, but good for sorting. And then we have to ask ourselves, what is the efficiency of this sort? Well, to put anything into a complete tree, put one node into a complete tree is at most log n. That's the upper bound, log n. So that's order log n. But I've got n of them to put in, so that it is order n log n to build my heap. And then it is also order n log n to delete my heap, which means that it is order n log n plus order n log n, which is order 2 n log n. So to build and then delete is of order 2n log n, which is the same as order n log n. And if you are confused about the math, that's okay, as long as you remember that it is order n log n sort, which compares with merge sort. Merge sort is also n log n guaranteed. This is order n log n guaranteed. Quick sort is order n log n most of the time, but it can deteriorate into order n squared. So this is a pretty good sort.